Okay, we're on photoelectric effect, and the key points I want to just work through in turn. So the first point is we're talking about light of a specific wavelength, which might be given as a frequency, we might have to work out its wavelength. It falls onto a metal, so it's only working with metals. Electrons fly off the surface of the metal with a certain kinetic energy, and we can gather those up using plates and other things and a voltage. And this will only work in a vacuum. Light of a certain wavelength falls on a metal, electrons fly off. Okay, and we can calculate that kinetic energy. So, next stage. Now, one way of looking at this would be, I don't need to kind of see my next diagram. So, one way of looking at this is to say light is waves, waves, and waves work perfectly well when we're actually talking about adding together wave energies, doing superposition, doing diffraction gratings. Waves work perfectly well. But the only way anyone's ever managed to explain the photoelectric effect is by having a completely different view of light and saying, no, light is not waves, it's kind of chunks of energy. Okay, and those chunks of energy depend a lot on the colour of the light. So here we go. So what I'm suggesting here is the packets of the energy they have is given by this equation. Energy equals a constant that we call Planck's constant times by the frequency. So if you've got a high frequency like blue light, that will naturally have more energy, and red light, lower frequency, longer wavelength, lower frequency. So that has smaller energy because it has smaller frequency. So I've tried to depict that in size and colour if you think about it. So the blue packet is a bigger energy packet. All the blue packets are the same amount of energy, and because the F is bigger, the energy is bigger. The red has a smaller frequency, so I've depicted it with a smaller letter, and therefore I get a smaller energy because the H is one of the most fundamental constants. Now, so E equals HF. Now, remember, because this is one of our most basic equations about waves, V equals F lambda. Now, if you're given a wavelength and you need a frequency, you do V over lambda equals F. So you do 3 times 10 to the 8 divided by your wavelength will give you a frequency. If you bundle it together, you could make an energy equation like this. The energy of a photon is h v over lambda. So as the wavelength gets bigger, because you're dividing by wavelength, the energy gets smaller. So the longer wavelength red, has the smaller energy. The smaller wavelength blue has the bigger energy. So I personally would just remember this because it's so basic and fundamental. That's the most important equation to remember in this section, I would say. And if you need to convert between wavelengths and frequencies, just do it. Just use V equals F lambda and we'll just convert. Okay, so now in that diagram, of course, the light was landing on the metal, and the metal is, so photons of light landing on the metal. Now the metal is holding on to its electrons, otherwise it would be not having any electrons. So in some way the metal is holding on to the electrons, and we kind of need to take the electrons off it, which is kind of a bit like the concept of ionization in chemistry. So the metal has to be given energy to release the electron, is one way of thinking of it, perhaps a more chemistry way of thinking of it. Or another way of thinking it is perhaps the electron needs energy to escape the attractive forces of the metal. Okay, and this energy is called the work function. It's an energy, so we'll measure it in joules. Okay, it's an energy, we will measure it in joules. So let's have a look at how the equation works out for this. So, well, let's have a look at the situation. Just for the moment, I'm going to explain in literally 2 slides time why I'm going to use HF0 for this. This work function is the phrase for the energy. And basically, the kinetic energy I can get at the end is the photon energy comes in, it hits the electron has to give up, it has to give some energy to get away from this binding. That's the work function. So the kinetic energy it has at the end, we're going to get that by just taking this energy and taking away the work done to release it from the metal. So I've written that as the photon energy has to become the energy to release it from the metal and the kinetic energy of the electron. So if I wanted to know this kinetic energy, I'd take that across the other side, and I have photon energy minus work function would equal the kinetic energy of the metal. Okay, I'll leave that there in case you want to come back to that when you do the problem solving. Okay. Now, just a little bit of an observation. Metals which are more reactive generally have smaller work functions because it's easier to take that first electron off them. And remember, photon energy is the highest for ultraviolet and blue light, violet light, and lowest for red light and infrared. These whole kind of categories of experiments can't really be done far outside. So you can't do this with like X-rays or gamma rays or anything, and you can't do it with radio waves or microwaves or anything. So you can only do it the way things are actually constructed in terms of shining lights that you've made with things that are not too far from the visible spectrum. Okay, so let's have a look at how this equation becomes a graph, because I think this is quite important. So, where's my equation sheet? Here's our equation. Now, if I plot this kinetic energy up the side of my graph, then the graph is quite interesting. So for a certain frequency, now it might have been easier for me to sort of illustrate this by using different colours, but say I take red light as being low frequency here. So at this point on the frequency scale, I want red. Now, at this point, the energy of the red light here, for this particular, the energy of the photon emitted is negative, i.e. it's not emitted. Okay, so the photon is still bound. I need to provide, for this particular system, this point on the graph, the x-intercept, marks the point where the frequency is the minimum frequency to release an electron. Okay, so only once the frequency goes higher than this point is suddenly we've got positive energy emitted. We actually have kinetic energy emitted in the electron. So this is a really important point on the graph. So if we were, say, at some sort of appropriately bluey, ultraviolet point on this, we'd find that our electron has this much kinetic energy, which basically means the photon that came in had enough energy to drag it from the very depths, because the point here on this energy scale where no light, the frequency is 0, so no light is hitting it, is in the metal. At that point, the y-intercept equals the work function. So this point on the graph is the work function. Now, to get light, to get a certain amount of emission, I need to provide enough energy to overcome the work function and a bit more to become the kinetic energy of the electron. So, now, because there's a certain magical frequency at which an electron is released, that's normally called the threshold frequency. And that's given an F0. So if you take Planck's constant and multiply it by the threshold frequency, you get this Planck's HF0, and that energy is the work function. Okay, so the work function, the amount of energy that the work function is Planck's constant times the minimum frequency at which an electron is released. So that's quite an important point that the work function is given by E equals hf0, and f0 is important, it's called the threshold frequency. And this is a kind of theoretical experiment because it's very difficult to get a light that you can vary the frequency of a light. So you'd have to do this with lots of different lights, maybe 8 different lights. And an actual experiment for this, which we're not going to do in school, would be you collecting a variety of different bits of data like this and trying to make up this line. And then when you made up the line, you could work back. You couldn't access this region of the graph. You couldn't do that experimentally. And you could do a variety of different frequencies, measure the kinetic energy of the emitted electron, and then do a line of best fit back to find this threshold frequency. Because, okay, I'm going to stop there and do a quick example. So light of wavelength 550 nanometers is incident on a metal. Perhaps I need a comment there. With a work function of 2.5 times 10 to the minus 19 joules. Find the kinetic energy of the electrons emitted. Now, I've written that badly because it's possible for the electrons to be emitted in strange directions or interact with each other, which would result in less kinetic energy being emitted. So we're really looking for the maximum kinetic energy. It's possible there'll be electrons that will come out with slightly less than this due to other effects, but we're looking for the maximum kinetic energy possible. Now, step 1. This question is a little bit awkward in that it's given us a wavelength when everything about this is about frequency. So I would start off by saying, okay, we need a frequency, so let's change it over. So V equals F lambda, lambda equals V over F, not useful. F equals V over lambda. Speed of light I know. Wavelength taken from there. Nano, 10 to the minus 9. So I get 5.45 times 10 to the 14 joules. Okay, that's good. I've now got a frequency, so I can move into the photoelectric effect equation. Standard photoelectric effect equation. Okay, photon energy, work function, kinetic energy. Remember, we're being asked for the kinetic energy here. So this is what we're interested in. Right then, so let's substitute in. So let's substitute in. Planck's constant, you see, here I've had to use Planck's constant from the book, 6.63 times 10 to the minus 34, times by my frequency from there, bring that in, that's my photon energy, that's the energy the photon brought in. The work function I've been given in the question is 2.5 times 10 to the minus 19, and this is what we're looking for. So on the next line, if you work that out, you get 3.61 times 10 to the minus 19, spot the deliberate mistake. And then all I need to do to get EK is then subtract, because these terms are added together, you algebra stars. I need to subtract. I've craftily done that in brackets to save me writing times 10 to the minus 19 twice. And I get my kinetic energy is 1.1 joules. Now, you've really got to be able to work around any way around this equation. So you can be given questions obviously to find any aspect of this on the understanding that you know what all the terms are in it. So I'll shut up and say at this point we can do the next page of the course questions. Okay, so let's go back to those course questions and do the course questions because the blue book doesn't offer as much in the way of challenge on this task.